Hello, this is Dr. Hassan with Innovate, and this is lecture number 60, Reduction of State Tables by Inspection, of Chapter 9, Design of Synchronous Sequential Networks, of the course Digital Logic Design or Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design. However, there are many books related to the topic and the course of digital logic design. In Chapter 9, we are concerned with the design and the implementation of synchronous sequential machines. And we said there are 4 main steps to design and implement a sequential machine. The first step is the derivation of state graphs, and the second step is the reduction of the state graph and state tables. Then we do state assignments, then we implement the machine. The implementation could be with hardware circuitry like flip-flops and gates, or it could be with programmable logic device, and at that time we'll use the VHDL language to design the machine and generate the netlist file. Then we download the machine on a programmable logic device. So those are the 4 main steps in the design of any sequential machine or synchronous sequential machine. Now, the second step, we said the reduction of state tables. And in the reduction of state tables, what are the benefits of the reduction of a state table? Once we complete the derivation of the state graph, we can generate the state table. We check the derived state table from step number 1 to detect and eliminate any redundant or equivalent states. Then the reduced state table can be implemented with minimal number of memory elements or flip-flop and less hardware. So the benefit of reducing the state table are really enormous, and we could reduce the hardware by many folds when we use this step. So this is a very essential step in the design process of synchronous sequential machines. Let's look at the redundant and equivalent states. Definition number 1. 2 states, Si and Sj, of a clock synchronous sequential network are equivalent if and only if each combination of values of input variables, their outputs are identical and their next states are equivalent. Very clear. So in 2 states we have Si and Sj. They are equivalent if they have the same outputs and if their next states for each combination of input variables, if their next states are equivalent. In definition number 2, we say states S1, S2 to Sj of a clock synchronous sequential network are equivalent if and only if for each combination of values of input variables, their outputs are identical and their next states are equivalent. So this is really a generalization to definition number 1 from 2 states to J number of states, to a large number of states. In definition number 3, an equivalence class is a set of states in which all states are equivalent. So the class of those equivalent states, we call it the equivalence class. In definition number 4, we say a state that is equivalent to another state is called a redundant state. And the reason behind this definition, when we have a redundant state, we can remove it without affecting the function and the results of the machine. So we can remove it immediately. And we can minimize the state graph and the state table accordingly. Now, there are 4 main techniques in reducing the state table and the state graph. And these techniques, also called algorithms, they are reduction of state tables by inspection, which I will concern in this lecture, reduction of state tables using the Melchior graph, which we will do it in the next lecture, the reduction of state tables using the implication table in the following lecture, the reduction of state table using the partitioning method. Reduction of state tables by inspection. The guidelines for the reduction of state tables by inspection are as follows. Inspect the state table for multiple rows that perform the same function and then remove the redundant states. So if we see a redundant state, we will inspect the table, and if we see a redundant state, we will remove the redundant state. Step number 2, we update the state table by replacing the removed redundant state with their equivalent states. We repeat step number 1 and 2 until all redundant states have been removed. So we do continuous inspection to the table, then to the reduced table, then to the reduced table, until the end, until we can give a proof that there is no other states can be removed. It means all the remaining states are unique and there is no equivalence left among the remaining states. So we have to prove that. And we'll see this in an example. We are given actually the following merely sequential network defined by the truth table shown. The network defined by the present states A, B, C, D, E, F, G, and H. So clearly we have 8 states, A, B, C, D, E, F, G, H, and we have the next state at x equals to 0 and x equals to 1, and the present output Z at x equals to 0 and x equals to 1. Now, we have to look carefully at this state table. We search for redundant state. We have to look at row by row. So the potential rows of equivalence, we have row A, B, because they have the same output, 0 and 1. D also, it has 0 and 1. E, it has 0 and 1. Okay, bingo. If we look at E, row E, the next state BC and the output 0 and 1. A, the next state BC and the output 0 and 1. It's very obvious that A is equivalent to E because their next states are the same, and if they are the same, they are equivalent. It's B, B, and under x equals to 1, we have the next state C, and the present state A, and for present state E, also we have the next state C under x is 1. So BC and BC 0, 1, 0, 1. So immediately we say A would be equivalent to E. In step number 1, I will remove E, and I will replace every E in the table with A because A is equivalent. So this will become A. This will become A. Okay? And the new table, so we say A is equivalent to E. I will remove E, and I'll replace every E with A. So the new table will be without E, A, B, C, D, F, G, and H. And we have again the next states and the present output at x0 and x is 1. We will inspect the table further. Again, the potential equivalence would be between A and B and D and F because they have all of them the same output, and also H, it has the same output, which is 0, 1. So if we concentrate on state B, the next state I have for state B is B when x is 0, means I will remain at the same state when x is 0, and when x is 1 I will go to A, and the output will be 0 and 1. In state F, I would have also F, under x is 0 I will go to state B, and under x is 1 I will go to state A. So I have the next state are the same, and the present output are the same. So I have BA and BA and 0, 1, 0, 1. So clearly that row B would be equivalent to row F. Or we say state F is equivalent to state B. So I can remove F and I can replace every F in the table with its equivalence B. So this will become B, and this will become B, and the table, the reduced table, will look like this. So I will remove F and replace every F with B, and I will have now 6 state A, B, C, D, G, H, and I will remove the F. The table will not have any F anywhere anymore. Every F became B. Now, again, we have the potential that A would be equivalent to B, equivalent to D, and equivalent to H. Are they? Because they have the same output by looking at the output. And we have C, and G may be equivalent because they have the same output. Let's look at B and D. B and D, B and D. B at x equals to 0 will remain in B, and at x is 1 we will go to A. D, on the other hand, at x equals to 0 will remain in D, and at x is 1 we will go to A. So the behavior of state B and state D is the same behavior, because at x0 we are remaining at the same state, at x is 1, and they have the same output. They have 0, 1, and 0, 1, and this is why we are looking at them for possible equivalence to start with. So therefore, once we say that state B and state D, they have the same behavior. They remain at the same state at x is 0, okay, and they go to state A at x is 1. So B would be equivalent to D. B would be equivalent to D. The same story actually with H. H also have the same behavior. H will stay, the next state will be H at x is 0, and it will be A at state at x is equals to 1. So we go to A. And the output will be the same. So clearly B and D and H, they have the same behavior. So we say B is equivalent to D is equivalent to H. B is equivalent to D is equivalent to H. I can remove D and H and replace every D and H with their equivalent state, which is B. Okay? So this will become B for an instant. This is H. It will become B. And this D will become B because I will remove. So the table will look like A, B, C, G. The next state B, 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 and C, A, B, A. Okay. So again, I have some literature write-up for you here, just in case, to avoid any confusion. We said B and D under x0 require the network to remain in the same corresponding state. That is state B loops back to itself with a 0 output, and state D loops back to itself with a 0 output. While when x is 1, both state B and D go to state A with 1 output. Therefore, we say state B and D are compatible pair, since their successors are also states B and D. So they are compatible because their successors are B and D. We are staying at B and we are staying at D, so they are compatible states. Hence, B and D are equivalent. Similarly, B and H are equivalent by inspection, okay, because also they are compatible states. They are compatible there. Therefore, B would be equivalent to D, would be equivalent to H. So I will remove D and H and will replace every D and H in the table with state B. So we came with A, B, C, and G, A, B, C, and G. What else? Let's look at this reduced table now. We have A, next state BC. We have B, next state BA, the same output, and we have G, next state BA. So clearly very obvious that BA and BA, B would be equivalent to G because they are redundant state. G is a redundant state. They are identical. This row is identical to row B, BA and BA. So we say that B would be equivalent to G, and I can remove G and replace G, which really does not show up anywhere, okay, if any, with a state B. So G can be removed, and I will have the following table. I will have three states: A, B, and C, the next state, BC, BA, and BB, and the output 0, 1, 0, 1, 1, 0. Now, can state A be equivalent to C? Absolutely not, because they have different output. Can state A be equivalent to B? Maybe, if their states are equivalent. The next state under X0 are BB, that's good news. But under X is 1, they are CA. And A is not equivalent to C. Just we said A cannot be equivalent to C because A has 0, 1 output and C has 1, 0 output. So therefore, A cannot be equivalent to B. It is impossible. So the table in front of us with three states is the optimal, minimal table of this machine that we started with and we reduced by inspection. This would be the end of this lecture. Lecture 60, which is reduction of state tables by inspection. Any table, we can reduce it by inspection. I thank you very much for listening. Please subscribe by clicking on the blue circle. Hopefully to see you soon. Sincerely, Dr. Hassan.